Welcome dear viewers. We are continuing the discussion on transition and inner transition elements. In this module, we focus on the chemistry of some selected components of transition elements. And the focus is on potassium dichromate, potassium permanganate, titanium tetrachloride and more salt. First of all, preparation, properties and uses of potassium dichromate. Potassium dichromate is a well-known compound with the molecular formula K2Cr2O7. It appears as a very beautiful orange colored crystal. First of all, the preparation of potassium dichromate. Dichromates, every dichromates are generally prepared from chromates. Chromates as such obtained by the combination of chromite ore with the sodium or potassium carbonate in the presence of oxygen or air as per this equation. 4FeCr2O4 plus 8Na2CO3 plus 7 oxygen produces 8Na2Cr4 plus 2Fe2O3 plus 8 carbon dioxide. The sodium chromate obtained in the above reaction is in the form of a solution and it is then reacted with the sulfuric acid to form the crystals of sodium dichromate. We wish to prepare potassium dichromate. Up to this step, we got sodium dichromate. The sodium dichromate is converted to potassium dichromate in the final stage by reaction with potassium chloride. The reaction is Na2Cr2O7, that is sodium dichromate, plus 2 KCl produces our required compound, that is K2Cr2O7 and sodium chloride. That about the preparation of potassium dichromate. Regarding the structure of chromate ion, that is CrO4 2 minus, and dichromate ion, that is Cr2O7 2 minus, are shown in the picture. The dichromate ion Cr2O7 2 minus can be considered as a dimer of chromate ion. Chromate ion as such is tetrahedral and the dichromate ion is having double tetrahedral arrangement. The tetrahedra connected through an oxygen. Then the physical properties of potassium dichromate. As I mentioned, potassium dichromate is an orange colored crystal. It is a crystalline solid. It is moderately soluble in cold water but highly soluble or easily soluble in hot water and it is not a deliquescent solid. Regarding the physical properties, the first property, thermal decomposition, that is potassium dichromate when heated above 500 degrees Celsius in the temperature range of 500 to 600 degrees Celsius, it will undergo thermal decomposition. That is, during heating, substance dissociated into several molecules. During thermal decomposition, the products obtained are potassium chromate, chromic oxide or Cr2O3 and oxygen gas is liberated during the thermal decomposition. Then action of alkali. On adding alkali like sodium hydroxide, the orange red of potassium dichromate changes to yellow color. The reason for this color transformation is due to the formation of chromate, that is potassium chromate. It is an yellow colored substance and the potassium chromate is obtained as per this equation. Potassium dichromate acts as a very powerful oxidizing agent, especially in acid medium. When we are reacting potassium dichromate with the concentrated sulfuric acid, nascent oxygen is produced. This is as per the equation. K2Cr2O7 plus 4H2SO4 produces K2SO4, Cr2SO4 thrice, that is nothing but the chromic sulfate, water and 3 nascent oxygen atoms are released. This nascent oxygen can be utilized for further oxidation reaction. So, this reaction between sulfuric acid and potassium dichromate forms the basis of powerful oxidizing property of acidified potassium dichromate. See, there are several oxidation reactions that can be performed by using acidified potassium dichromate. For instance, this acidified potassium dichromate oxidizes iodides to iodine. Simply, potassium iodide can be oxidized to iodine. This is the basic reaction where oxygen is released as nascent oxygen. By utilizing that oxygen, potassium iodide can be oxidized to iodine. So, 2 Ki plus H2SO4 plus 1 nascent oxygen, we will get K2SO4 plus water plus iodine. So, in the first reaction, there is the liberation of 3 nascent oxygen. Such that to get a balanced equation, we can multiply the second equation by 3. Because in the first equation, there are 3 nascent oxygen and only 1 nascent oxygen is utilized for the reaction shown in bracket. That's why we have to multiply with the 3 to get a complete balanced equation. Next oxidation reaction. This acidified potassium dichromate oxidize ferrous sulfate to ferric sulfate. Again, this is the basic reaction. The nascent oxygen liberated during the reaction is utilized for the oxidation of ferrous sulfate to ferric sulfate. Ferrous sulfate oxidation to ferric sulfate occurs again in the dilute sulfuric acid medium. Acidified potassium dichromate oxidizes hydrogen sulfide molecule to sulfur. Hydrogen sulfide is a rotten smelling gas. We are familiar with that. That hydrogen sulfide can be converted to elemental sulfur by using the oxygen produced in the above reaction. This acidified potassium dichromate also perform the oxidation of sulfur dioxide gas to sulfuric acid. This is the equation responsible for that oxidation. SO2 plus water plus nascent oxygen produces sulfuric acid. In another reaction, acidified potassium dichromate oxidizes sodium sulfite, that is Na2SO3, to sodium sulfate. This is the equation responsible for that oxidation. Na2SO3 plus nascent oxygen that we got from the first reaction produces Na2SO4. Now, another important reaction of potassium dichromate, that is the chromyl chloride test. Chromyl chloride test is a test for chloride. It is a confirmatory test in qualitative analysis. When a soluble chloride like a sodium chloride or potassium chloride is heated with the potassium dichromate and concentrated sulfuric acid, we will get orange red vapors of CrO2Cl2, that is chromyl chloride. This is the reaction responsible for the production of CrO2Cl2. The production of CrO2Cl2 confirms the presence of chloride salt. Now, the reaction of potassium dichromate with hydrogen peroxide. Acidified solution of potassium dichromate develops a blue color with the hydrogen peroxide. The blue color is due to the formation of a chromium compound, that is CrO5, as per this balanced chemical equation. K2Cr2O7 plus sulfuric acid plus 4 hydrogen peroxide gives K2SO4 plus 2CrO5 and 5 molecules of water. Now, reaction of potassium dichromate with K2CO3 or potassium carbonate. K2Cr2O7, when reacted with the calculated quantity of K2CO3, we will get yellow crystals of potassium chromate. That is, the orange color of potassium dichromate changed to yellow color due to the formation of K2Cr O4. Action of hydrochloric acid. Potassium dichromate, when treated with the concentrated HCl, chlorine gas is liberated. That is, this is a kind of oxidation reaction. HCl is oxidized to chlorine gas as per the balanced chemical equation. Now, reaction with the carbon. Potassium dichromate is also reacting with elemental carbon, and the product of the reaction is Cr2O3 or chromic oxide. This reaction is as per the balanced equation K2Cr2O7 plus 3 times carbon and a molecule of water. The products are 2 Cr2O3, 2 potassium hydroxide and 3 molecules of carbon monoxide. This about the preparation properties and reactions of potassium dichromate. Moving on to next compound, that is potassium permanganate. Potassium permanganate is a purple black crystalline solid that dissolves readily in water to produce intense pink or purple colored solution as shown in the picture. Potassium permanganate is prepared by using pyrolusite or MnO2 as the starting compound. MnO2 fused with the KOH in the presence of air, potassium manganate or K2MnO4 is obtained. The potassium manganate obtained is then oxidized by chlorine to get to potassium permanganate. This is as per the equation 2K2MnO4 plus chlorine gas gives 2KMnO4 and the side product is potassium chloride. Now, physical properties of potassium permanganate. As we are aware, potassium permanganate is a purple colored substance with a melting point 523 Kelvin, fairly soluble in water. The central atom manganese in KMnO4 is in sp3 hybridized state, that is a tetrahedral geometry it follows. Then regarding the structure of KMnO4 central atom manganese is sp3 hybridized, hence tetrahedral arrangement, that is the 4 oxygen atoms of KMnO4 are tetrahedrally arranged around the central atom manganese with the bond angle nearly 109 degree 28 minute. The second picture is the ball-and-stick model. The first one is the bond line representation of potassium permanganate. Chemical properties of potassium permanganate. First of all, action of heat. Potassium permanganate, as in the case of potassium dichromate, there is susceptible to thermal decomposition. On heating above 200 degrees Celsius, oxygen gas is liberated from potassium permanganate. This is as per this equation 2KMnO4 produces K2MnO4 plus oxygen. That is the product of the reaction is potassium manganate and oxygen gas is liberated. When an alkaline solution of KMnO4 is heated, instead of taking pure KMnO4, if we take an alkaline solution of KMnO4, oxygen gas is again evolved as per this equation. Here also the products are potassium manganate, oxygen and also water. Reaction with glycerin. This is a very popular reaction. In this reaction, let we mix some quantity of potassium permanganate with very small quantity of glycerin. The reaction demonstrates powerful oxidizing property of KMnO4. When these two substances are mixed together, huge amount of heat is liberated and that causes glycerin to ignite and burst into a flame. The chemical reaction occurs by the balanced form 14 KMnO4 plus 4 times glycerin gives K2CO3, that is potassium carbonate, 7 times Mn2O3 manganese oxide, carbon dioxide and 16 molecules of water. The huge amount of heat liberated during the reaction leads it to fire formation. Oxidizing property of potassium permanganate. As in the case of potassium dichromate, the KMnO4 in acidic medium is also a very powerful oxidizing agent. In neutral medium as well as in alkaline medium, KMnO4 is a powerful oxidizing agent. Thus, in acid medium, neutral medium or alkaline medium, KMnO4 can perform as oxidizing agent, and the most powerful action is in acid medium. What happened in acid medium? When potassium permanganate mixed with the sulfuric acid, A reaction occurs like this and 5 nascent oxygen atoms are liberated. That nascent oxygen atom can be used for oxidation reactions. In alkaline or in neutral medium, 3 nascent oxygen atoms are liberated. So, based on the number of oxygen atoms liberated, KMNO for an acidic medium is a powerful reducing agent compared with other media. In acid medium, we have the reaction showing the liberation of 5 nascent oxygen. By utilizing this nascent oxygen, several oxidation reaction can be performed. For instance, acidified KMNO4 oxidizes ferrous sulfate to ferric sulfate. It oxidizes oxalic acid to carbon dioxide. Oxalic acid is COH twice or H2C2O4. It is converted to carbon dioxide and water. The reaction between oxalic acid and potassium permanganate forms the basis of redox titration in volumetric analysis. Now, another oxidation reaction. Acidified KMNO4 oxidizes potassium iodide molecule to iodine. That is, when potassium iodide is treated with KMNO4 in acidic medium, iodine gas is liberated. It oxidizes sulfate to sulfate. It oxidizes nitrite to nitrate, and several oxidation reactions are there. Now, as I mentioned, the reaction between oxalic acid and acidified potassium permanganate forms the basis of volumetric analysis. What we are doing in volumetric analysis? In volumetric analysis, we are finding out the concentration of a solution by using a solution which is a standard solution. That is a solution with the exactly known concentration. Here, KMNO4 is taken in the burette. A solution of oxalic acid is taken in the conical flask. After the titration, there we will get an end point, which is the appearance of a very pale pink color that indicates slight excess of KMNO4 during the reaction. The volume of KMNO4 used, volume of oxalic acid used, and any one of the concentration, we can evaluate the concentration of the other substance, and this forms a very important reaction in volumetric analysis under the title permanganometry. Now, the reaction between oxalic acid and acidified KMNO4 shows an interesting aspect, that is nothing but attocatalysis. Suppose we are performing the reaction between oxalic acid and KMNO4. The reaction is very slow initially, and the reaction is as per the balanced equation. But after some time, when the reaction proceeds to some time, we can see a very increased rate, or the reaction proceed now very fast. What is the reason for this? One of the product, manganese sulfate, MnSO4, act as a catalyst for the future reaction. So, during the starting of the reaction, rate of the reaction will be very slow, but after some time, the reaction will move very fast. The reason is, one of the product, MnSO4, act as a catalyst for the future reaction. So, product as such act as a catalyst, and that is termed as attocatalysis. So, phenomenon of attocatalysis is observed in reaction between acidified KMNO4 and oxalic acid. Another oxidation reactions of alkaline KMNO4. I mentioned alkaline medium also KMNO4 is a good oxidizing agent. Some reactions are here. Alkaline KMNO4 oxidizes iodides to iodate, that is potassium iodide is converted to potassium iodate KiO3. It also oxidizes ethylene to ethylene glycol. Another compound for today's discussion is titanium tetrachloride. This titanium tetrachloride is very famous since it involved in the preparation of a catalyst for polymerization, that is called the Ziegler-Natta catalyst. Titanium tetrachloride is an important compound of titanium. It is a volatile liquid, upon contact with humid air, that is whenever we are opening the bottle of the solution containing the solution of titanium tetrachloride, it forms opaque clouds of titanium dioxide and hydrated hydrogen chloride, that is fumes will come out. Preparation of titanium tetrachloride. Several methods are available for the preparation of titanium tetrachloride. Let us see some methods. The first method, by heating rutile, that is titanium dioxide, or with carbon in a current of chlorine. As per this equation, TiO2 plus carbon plus 2Cl2, you are getting titanium tetrachloride and liberating gas is carbon monoxide. By the direct reaction of titanium dioxide and chlorine, we will get titanium tetrachloride. Then chemical properties of titanium tetrachloride. Titanium tetrachloride is a molecule which will undergo very rapid hydrolysis. Hydrolysis means the reaction with the water. As a result of hydrolysis, TiCl4 is converted to titanium dioxide. It is a strong Lewis acid. It can form complexes with Lewis base. Lewis acid is electron pair acceptor. Lewis base is electron pair donor. It can form complexes with Lewis base like ammonia. For instance, TiCl4 can form TiCl4 6NH3 or TiCl4 8NH3. They are Lewis acid base compounds. Reaction with silver. This is a reduction reaction. Titanium tetrachloride is reduced to titanium trichloride and liberated substance is AgCl. Now the reaction with hydrogen fluoride. Hydrogen fluoride converts titanium tetrachloride to titanium tetrafluoride. Then reaction with magnesium. This is a very important process in the metallurgy of titanium. Titanium tetrachloride can be reduced to elemental titanium by using magnesium. This reaction is termed as the Kroll's process. Now the last compound in this presentation is more salt. More salt is also referred as ammonium iron 2 sulfate. It has the chemical formula NH4 twice, FeSO4 twice, H2O 6 times, or simply we can put 6H2O. It can be characterized as a double salt. The reason is simple. It constitutes two salts, namely ferrous sulfate and ammonium sulfate. We are familiar with alums. They are also double salts. It is a reducing agent and a primary standard in volumetric analysis. Then what is a primary standard? A substance used to prepare standard solution. A standard solution is a solution with exactly known concentration. So, a substance used to prepare a standard solution is termed as primary standard in volumetric analysis. This more salt is a reducing agent as well as can act as a primary standard, can be used as a primary standard in volumetric analysis. Regarding the preparation of more salt is by mixing ammonium sulfate and ferrous sulfate solutions in an equimolar ratio, but the solution must contain traces of sulfuric acid. The solution is then subjected to crystallization process. The crystallization process leads to the formation of green crystals of more salt. Dilute sulfuric acid is generally added to more salt. This is because dilute sulfuric acid prevents the hydrolysis of ferrous sulfate. This more salt reacts quantitatively with oxidizing agents such as acidified KMnO4, acidified potassium dichromate, etc. and highly useful in volumetric analysis. Acidified KMnO4 is an oxidizing agent due to the reaction 2 KMnO4 plus 3 H2SO4 gives K2SO4 plus manganese sulfate plus water plus 5 nascent oxygen. That nascent oxygen can be used for oxidation of more salt. That is, more salt is a reducing agent and acidified KMnO4 is an oxidizing agent. The redox reaction between them is shown in the balanced form as this. And as per this balanced equation, we can quantitatively react acidified KMnO4 and more salt. This forms the basis of redox titration in volumetric analysis. Thus, in this session, we have discussed preparation properties and applications of 4 important compounds. They are potassium dichromate, potassium permanganate, titanium tetrachloride and more salt. That all about this presentation. Thank you.